or rules of operation are basically tell us the constraints under which the system operates, and also it tells us the relationships, okay, the mathematical relationships that we have. So for example, one of the laws of the car is if you press the accelerator, the car accelerates, goes faster, right? So that's the rules of operation, and there's a law, and the law says presumably that if this is the accelerator pedal, and this is the distance between the accelerator pedal and the floor, and that's x, and let's say we start 0 over here, and this is going to be some value m. So we just say the law says that 0 is less than x less than equal to m, and then v is equal to some function of x, where v is the velocity, and if you're lucky, f is linear. We can assume it to be linear anyway. Let's hope. Okay, if it's not linear, I'll tell you what to do in a minute, but we can assume f is linear. Okay, so now we have a model, right? It's the laws, and the laws. This is the law. Okay. Any questions about this over here? Yeah.
Why did you choose zeros to above and
Beg your pardon?
I think you have to exchange the place of 0 and m.
Why? This is the accelerator pedal, right? It's a pedal that's sticking like this. When it's 0, and then I go all the way up to maximum. Yeah. So this is the accelerator pedal, right? So, okay, so these are the laws, and then finally we have to do step 3, and do I need this? I think I'll keep it. So step 3 is over here. Step 3 is the control goal. What is the control goal that you want to achieve? Okay, so in the case of the accelerator, of the speed, I wanted to achieve a particular control goal, which is achieve a particular velocity, okay, a particular speed. So, and then you want to say what is the error, allowed, permissible error. Sometimes you have that, what's the tolerance? So I can have the speed, and I'm okay with plus minus, 1 meter per second, plus minus 10 meters per second, whatever. That's the error, and that's a tolerance that we want to try and have. So basically, what happens is in this step we're getting the variables of the system. In this step we're finding the relationship, right? So the variables are x in this case, okay, v, okay. So that's the effort, that's the flow. We got that x and m, x and v, and then we got over here the rules which govern what v, and presumably we have 0 is less than v less than equal to some v max. Okay, so you can't go faster than some. V max is certainly, the speed of light. So we have some V max. Okay, so no car can travel faster than the speed of light. It's an obvious V max, but maybe there's other V max as well. And so we can, get this. And then the last thing we say, okay, and we want the V to be equal to some V ref, okay, plus minus error. Error could be proportional error or absolute error. It could be plus minus 5% or plus minus 10 meters per second, whatever. So that's it. So that's the process we go through. And I've gone through a number of different kind of examples, mostly the speed example here, but referred to other systems. The only way to actually do this is to try it out, and use it. So presumably you'll be using some aspect of control theory in your work, and if you are, then you should take your system, whatever that is, and apply this and see what happens. Okay. Any questions about this? Because this is sort of the touchy-feely part, and then after that, once you get into the math, it's really, it's just math, right? But the math is driven by this, okay? And that's so, in some level, what we do with the math is to make more precise, make concrete these concepts, vaguer notions. But the success of the system depends on these vague notions and getting them right the first time, or at least getting them right the second or third time. Okay, so yeah. Okay, all right. I'll just add a comment over here. I was reading an obituary of Steve Jobs, and what did he bring to Apple? What did he bring? He was not a computer scientist, In fact, he never finished in college, right? His main thing he learned in college apparently was calligraphy. That's what he learned, and design. But he understood the system and its component parts. The system here was not the iPod or the iPhone or the iPad or the anything. The system was consumers. And the relationship, the component parts, what makes you tick, what makes you pull out your wallet and buy stuff, okay? That's what he understood, okay? And so he was able to get the control goal. What is his control goal? Okay.
Empty our pocket.
No, that was a part of the control goal was to make Apple the richest company in the world, okay? That's basically it. Make it the most, and so the error was, whatever, plus minus $1 billion. Okay, who cares? Okay, so that was the control goal. But he had this big system where he could drive these smaller systems, all the engineers and so on and so forth, build this little control system so that at the end, this is what he really understood, the component parts and relationship. That's why I said it's complicated, right? If you figure it out, then you're Steve Jobs. You figured out what aspect of the design makes it intuitive. Okay, what does it mean to have an intuitive user interface? Okay, maybe he didn't have a mathematical modeling of it, but he knew enough to basically drive the next level down and say, okay, now your goal is to have whatever it is, a system where you only have one button mouse. That's it. So, but where did that come from? Well, that came from this part over here. What makes something easy to use? Okay, and that's what comes from here. So, the three ways it turns out to mathematically represent a system, and two of them are actually very useful, and I'll explain one of them. One of them is sort of just a transitional thing. So, the first one is what's called the state space approach. The second one is called the impulse response. And the third thing is called the transfer function. The state space approach is the most general approach, and it's actually what is also used in what's called modern control. So modern meaning it was done in 1950, so it's pretty modern compared to the earlier approaches which was done in the 1920s by and large. So that's why I put modern in quotes. The impulse response approach is basically a transitional one to get to the transfer function, and we'll actually focus on this for the most part. And the transfer function is for single input, single output systems. The modern one can handle multiple input, multiple output, as well as time varying. Okay, so that's sort of a preview into the three approaches, and we'll look at all three. Okay, so let me start with the state space approach. The state space approach, the most important part of that is to identify what I call the state variables. And these are denoted by vectors. So for this lecture, I'm going to denote vectors in color. So I got my high-tech equipment here. So we have x of t, and t is a scalar. So oops, okay, there. So x is a vector, and so you have a set of state variables. And the intuition here is that if you knew the values of the state variables, then you know everything about the system. Everything about the system. Okay, so in the speed control car example, I have the accelerometer position where the pedal is, and I have the velocity, and that's it. If I know the pedal position and know the velocity, essentially nothing else about this car matters. It doesn't matter what color it is, what size, what shape, how many passengers. None of it makes a difference. I just need to know the pedal position, I need to know the velocity, and I'm done, right? So that's why I call it the state variable. In the case of a computer system, we can often represent the computer as going through some kind of finite state machine, it's some kind of states, okay? And this is a very popular way of representing and modeling computer systems using a state machine. If you have a state machine, then the implicit assumption is that when the computer is in a particular state, then we know everything about it in that state. Okay? And so the identity of the state is in fact the variable that we care about. So it's in state 5, state 2, state 10, in which case the state variable is just basically I am in the state number in the finite state machine. That's the state variable. Okay? So in a computer system, it's a relatively straightforward thing. And in other systems, the modeling effort at the end of the day is going to tell you what are the state variables. Okay? And that's denoted by x of t. Okay? Generally speaking, if the number of state variables corresponds to the number of energy elements. So I talked about energy storage, passive elements. So the number of passive elements tells me how many state variables I need, because I want to tell you the status, how much energy is stored in each passive element. In a computer network, storage elements are buffers, right? If I have 10 buffers, I have 10 storage elements, and I need to know how much capacity, how much is filled up. So I need 10 state variables, one for each buffer in the network. At least 10 variables, maybe more, right? But I need at least 10 state variables. So that's the notion of this is a state variable. The second, and this is a column vector. So this is a column vector. The second thing is the oh, I'm sorry. I need to tell you something more. The dimension. So the dimension is called the order of the system. So if you have 10, it's a column vector of dimension 10. It's called the order. And right. Okay. Right. So I was talking about the web server example we talked about last time. If you remember that, we had some client or the browser or whatever, and then we had a buffer, and then we had the server, web server. So we have one buffer over here. So we need basically one state variable, which is the buffer size, which you can call x over here. Okay. Now the order says, okay, so that we have, okay, so let's look at a case of a single input, single output system. Then in the case of single output system, we only have x of t, because this is single input, single output. Okay. And so I'm sorry. Take it back. So the state variable is a column. The input is u, okay, which is this thing over here. That's u. So the plant is going to be represented by x. Okay, the x over here, and I have to use a. The state of the plant is represented by the column vector x. That's what I have over here. The input is u, and that's a scalar, and the output is y, that's a scalar in case of a SISO system. So if it's SISO, input is u, and the output is y. In the case of a MIMO, the input is the vector u, output is the vector y. So I just remember, okay, I just realized I misspoke. For the car example, the speed control, v is the output, the velocity is the output, it's not the state. The state is just the accelerator position. Okay, that's where we are at that. Okay, anyway, to come back to this, and then we have a disturbance. In the case of single output, and in the case of a multiple output, you have w, and just to keep things straight, I'll show the state. In both cases, you can have vector. Okay, so SISO only means that the input and output are scalars, not that the state variables are scalar. Okay, you can have very large number of states, internal states, state variables, but just the input and output are going to be like so. Okay. Any questions about this over here? So in this case, the state vector. The state space representation of the system says basically we want to determine how the state changes over time. Okay, and the way we do it is by looking at the first derivative of the state variable. Okay, we want to basically compute x dot. Okay, and we'll write it like this. We'll break it up into x1 dot. So the first state variable changes like this. A11 x1 plus A12 x2 plus nxn plus b1u plus f1w1. Okay, and then x2 dot equals 12x1 plus b2u plus f2w2, and so on. So what happens is that essentially we are describing how each component of the state is going to be evolving as a linear combination, okay, of the prior state. So this is true for a LTI system, which I forgot to mention. I'm assuming the system is LTI. If the system is linear and time invariant, then we can write this. So it's an1, not n1. Ann xn plus bn u plus fn wn. So, and in the matrix form, we can just write this as x dot equals a x plus b u plus f w. Okay, so that's the state update equation. So we're basically saying, if I have a state, I can tell you what the rate of change of that state is depending on what input I get and what the current state already is. And then the output equation, y is going to be scalar. So y equals the vector c multiplied by x plus du, because u is a scalar, plus why do I have t? Oh yeah, TET, because E is going to be a column vector of, I didn't write down what y is, but y is given by y equals C1 x1 plus C2 x2 plus. So it's basically some linear combination of the Cn plus the disturbances. And so I need to put a transpose because I want E to be a column vector. So if you go back to here, what I'm saying is that this y depends on the state variable x, plus it depends on the w, and it's additively coupled to both the x and the w. And that's where we have the equation, output equation for y. And then this box over here is actually the same equations in vector form. Okay? Any questions about this over here? Yeah.
What is C?
C is this one over here, C1, X1, C2, X2. For the output, A is the way the state updates, and that's the output. So this is state update equation.
I'm talking about the vector.
C, this one. That's C1, C2, and so on. That's the vector of, I guess it should be CT. Oops.
Exactly.
Yeah, sorry. Okay, that's a typo in the book as well. Thank you. Right. Okay.
What is DU?
Du. Oops. D is there should be a y depends. Wait a minute. D is the input u. So y depends on u. See, y depends on w, x, and it may depend on u as well. Just like x may depend on u, y may depend on u as well. So there should be a. That's excellent.
So it's some D is some scalar.
Some scalar. Yeah, whatever. So it's some. I mean, this is the most general form, basically. So yeah, that's a du. Yeah.
Are both f and w vectors?
In the general case, yes, f and w are vectors.
Is that the multiplication?
F and w, yeah. So this was basically f1 w1 plus f2 w2 and so on, f and wn. So this is going to be. Let me see. So what am I going to make this? So w would be a column vector, and I suppose I should make, to be consistent, I should make this. Yeah, that's fine. They're both column. Let me see what I want to do here exactly. I want to say that I want to get this one here, and so FW. I doing this right? So x1. So I don't want the dot product basically, right? Because I don't want ftw, that would sum it all up. I just want f1, w1, f2, w2, and so on. So I'm trying to think, is this the right way to do it? Yeah.
You just say it's element-wise multiplication.
Yeah, it's element-wise multiplication is what I want, but I think I don't have the right notation for it. Yeah, let me. So, okay. Okay, I'll get back to you on that. Let me. So the most textbooks basically just ignore the disturbance input, but it turns out you need the disturbance input if you aren't putting the disturbance into U, which is what is also done. And I kind of added that, but I realize now that that was not a good thing to do. So, I'll fix it and get back to you in the next class. So who asked me that? Okay, sorry about that. Yeah, I'm going to put a big question mark here, and I'll fix it. Okay, but it's basically notation. What we really want, what we really care about is this over here. So for y it works, ETW works for y, but for x it doesn't. For x it doesn't, because I want to do the, yeah, this is a bit messy. Okay, anyway, and what I was going to say, what the solution for the homework was to do this, okay, and make this, for the multiple input, multiple output case, you basically just, you just have vectors for y and u, and then you get multiple input, multiple output. But the disturbance stuff, well, if you ignore the disturbance, certainly this is correct. Okay, but if you have the disturbance, it gets interesting. Okay, I'll think about it. Right. The other thing I want to mention over here is these terms over here, A11 versus, let's say, A12. Just compare the two. In this case, what's happening is that we're saying that x1 depends on the prior value of x1. Okay? Whereas in A12, we're saying x1 depends on the prior value of x2, a different state element. Okay? So this term actually is how x2 influences x1. Okay? And if you look at the matrix, these terms, which are the self-evolution of the state, are the diagonal terms. Okay? So if you have a matrix which is only diagonal, okay, only diagonal elements, then each state element evolves independently of the others. Okay? And we'll call that a decoupled system. So each state, you can actually view this as being separate systems, because each state element is just doing its own thing. It doesn't really care what anybody else is doing, right? You may as well view it as n separate elements. However, the A12 is now essentially causing you a coupling between x1 and x2. So this is called the off diagonal or the coupling elements. And what we'd like to do is to minimize those. Okay? And if you remember the similarity transformation, what we did there was to take a matrix and to essentially diagonalize it. Okay? And we said that if it has non-repeating eigenvalues, we can easily take any matrix and make it into a diagonal matrix if it has non-repeating eigenvalues by using similarity transformation. And so here, that's what we're going to do. We're going to take a system, and then we can diagonalize it. And what happens is that then each element of x is going to be replaced by a different state element, which is some funny state element, not the original state element, but these funny state elements are going to be independent of each other. Okay, so we can study the evolution separately, and that's why the diagonalization becomes such an important step. And we'll study this a bit more detail later on. I just want to give you the intuition of what's going on. Okay, yeah?
For the multiple input, multiple output case, what is the number of input vectors? What is the number of inputs?
It's up to you, right? I mean, you can have m inputs, whatever, some value m, some vector.
It has no relation to the number of state variables.
No. You can have as many. You can have one or two inputs. You could have a million state variables, right? It's completely independent. Yeah. Okay. So I'll come back to this whole diagonalization later on. Let's look at the state variable representation of the web server, just as an example over here. So in the web server case, which I guess I didn't give it here, so we have some client, and then you have the buffer, and you have the server. This x is going to be the buffer size. That's the state variable I choose. That's, you can, of course, there are many different other things you could choose as well. You could choose x dot, or defines x, the rate of change of the buffer as a state variable as well. But buffer size is obviously a simple way of doing it. I have some input rate u, and I have some service rate. If you recall, I model as disturbance w. So the state space equation is just going to be x dot equals u minus w, where u is a scalar, w is a scalar, x is a scalar, right? So that's the state equation, state space equation of the web server. So I'm just telling you how the state changes. Now, this is actually not true, because obviously if the buffer is 0, right, and nothing is coming in, there's going to be no change, right? Or if the buffer is full, then I have a max criterion. I have to, so basically it has 0 less than or equal to x less than or equal to some value b. But if I ignore the boundary conditions, I can't go below 0 and I can't go above some max b. This is the state equation of the system over here. And y happens to be equal to x, because the output is, for our purposes, the same as the buffer itself. Okay. So one thing. So any questions about that? Okay. So one thing that's good about this kind of approach is that we can generalize from a single input to a multiple output system like this. Multiple input, multiple output system like this. The other thing we can also do is that we can make this time varying by making these functions of time. Okay, for example, if I make at, x, and b and dt also functions of time, then the whole system is time varying as well. So the system kind of transforms itself over time. Of course, it makes it basically impossible to analyze, but at least we can represent it, right? What this really means is that this matrix A changes over time. So at some point in time, A may be diagonal, so it depends on these elements, but later on maybe it depends on something else, on the other elements, and so on. And so at least the representation is straightforward. Okay, and of course A may be nonlinear. If you have AT, where we can also make this to be a nonlinear system. So actually, to be more precise, if I choose this representation, so there I have a linear form. This is a time varying linear form, and if I choose this variable representation, sorry, I have to use x dot equals some vector f of x, u, w, then this one is the most general form. F can be nonlinear as well. And similarly, y would be some g of x, u, w. Then this is any old system, right? But all we've done is that we've got x and y pulled out as a state variable in the output equation. Now, in many cases, even though the system is not linear, we can linearize it, okay? So remember that over here, the system is actually not linear because of the boundary condition. At the boundary condition, this equation doesn't actually hold, okay? We have some, anytime there's a max or a min, it's not linear. That's a rule of thumb. But if you find a max or a min, it's not linear, okay? Why? Is because it does not obey superposition. Okay, if you take two things, the output is not going to be the same, because I have a max, I can't go above that, right? So we can do what's called a linearization using the Taylor expansion. And so the Taylor expansion is of a simple function, if you remember f of x, let's see, so f of x minus x, let's see, f of x minus x dot, so f of x dot plus f prime. How do we do this? Okay, I'm trying to remember the one-dimensional. So, okay, so we want to say f of right? X minus x dot equals f of x dot plus x minus x dot f prime x dot plus x minus x dot square root 2 factorial f. So this is the standard Taylor expansion. So given, if you want to find out basically what is the value of a function at near some point x, near some point x dot, we can expand it in this way. Okay. So the interesting part is if we ignore all these higher powers of x, we basically are left with just a value at fx dot plus some term multiplying the first derivative of x evaluated at the value x dot, which is again some number. So it becomes a linear function of x. Okay, because these are constants and this is something multiplying x. Right. So that's linear. If you ignore all the higher terms. So if the higher order products can be ignored, right, then we can say that this is quote unquote linearized. So the intuitive explanation is we have some curve which is f of x, and we choose some point over here at x dot. In that small neighborhood, we can take the slope f prime x dot multiplied by the gap, and then this value over here at some value close to x dot, this is given by the tangent to that point. Okay, so it's linear because it's a straight line. Tangent is a straight line. So no matter where we are, we can always approximate it using these small tangents as long as sort of quote unquote close enough. So this is the linearization of a nonlinear function. Obviously this function is nonlinear, but at a particular point it looks linear. Okay. So in the same way, we can take a nonlinear system like this, and if these are analytical, we can actually compute the first derivative of f and g. We can actually represent the system using a linear approach, and this actually is generalizable to multiple dimensions as well, using the notion of a gradient. And I'm not going to explain the gradient, but for those of you who've seen it, basically we can say f of x minus x dot. Sorry, so I have the wrong left-hand side here in what I have over here. But essentially, what I have is going to have x. Oops. X dot u dot w dot, and this is going to be plus x minus x dot transpose gradient x f plus gradient of u in f plus So what we have essentially is the multidimensional version of the Taylor expansion, where the f prime has been replaced by the corresponding gradient with respect to x, u, and w of f. Okay, and the same thing can be done for the g as well. So again, in most cases, we will, at least in this class, we will be dealing with single input, single output systems. So these gradients are not relevant, but the gradient is basically just a generalization of a derivative applied to a vector. Okay, and so we're looking at the slope with respect in all the corresponding subdimensions. Okay, so I'm not going to, and this gives us the appropriate operating point. Okay, that we want to look at, and this is actually going to be x, right? Because it's x dot is going to be this. This is the x dot. I would say approximately equal to this. Yeah, so actually I don't have this right, because x dot is f, x, u, w, so at the operating point, so we should say x dot at x equals x naught is given approximately by this, and that's going to be the linearization of the system. So in almost all practical cases, we will not have a linear system. We'll have a nonlinear system to work with, and what you'll have to do is to choose the operating point such that it makes reasonable. It's reasonable to linearize around that region, and then you can use a linear system instead. So, though we study only linear systems, we know that systems aren't linear. But we hope that we can choose a point that's linear. In this practical case, what that would mean would be to choose the operating point to be where the buffer is neither full nor empty, but somewhere in between. Okay, then we can have a linear system around it. If we choose the buffer set point to be 0, then it's a nonlinear regime. It's very close. It's actually nonlinear already over there. It's close to the buffer capacity B. Then that's nonlinear over there as well. So in order to study it using control theory, we probably want to set X to be like B over 2 or something like that. All right. Are there any questions about this? Okay, it looks like I also run out of time. So I'm going to stop here. And then with next time, we'll talk about the impulse response transfer function and, yeah, okay.